Module 1, Lecture C, Strings and Input. By the end of this lecture, you will be able to use strings to label engineering inputs, outputs, and project information, collect user input and convert it into numeric values for calculations, and format computed results so they are understandable in engineering reports. String labels, project labels. Project labels make engineering scripts easier to understand, share, and verify. In Python, strings can describe things like a project name, dataset, or test location in human language. Clear labels give calculations context, making results more traceable and useful in professional engineering work. Clear project labels help people understand the context of engineering analyses and keep measurements tied to the right scenario. Labels may identify things like samples, test conditions, or design alternatives, but they do not affect calculations. Their main purpose is to reduce confusion, make comparisons easier, and ensure results are interpreted and reused correctly. Using project labels in Python programs helps make engineering reports clearer, more consistent, and easier to reuse. By updating key identifying details such as project names, dates, test conditions, zones, or equipment groups, the same script can support different projects while keeping results organized. These labels add context to raw data, improve readability, and make outputs more reliable for both technical and non-technical audiences. Python code. Project labels. Strings help make engineering results easier to read by providing clear project labels and context for calculations. Well-written labels reduce confusion in reports. The setup defines 3 text labels that give the engineering report its basic context: the project name, Riverbend Pedestrian Bridge, the responsible engineer, A. Patel, and the report type, preliminary deflection check. These labels help identify the project, assign responsibility, and clarify the purpose of the report. The analysis assigns clear labels to key items: the main span, the service live load, and the reinforced concrete deck. These text labels identify the structural span, load case, and material, so later engineering results are easier to understand and interpret. The project records 3 key design values: a span length of 48 feet, an estimated deflection of 0.62 inches, and an allowable deflection of 0.80 inches. These values define the structure's scale, its predicted bending under load, and the maximum permitted deflection for safe performance. They will be used to compare the expected behavior against the design limit. The code prints a simple project labels report that introduces the key context for an engineering report. It displays the project name, the engineer responsible, and the report type, organizing these details in a clear, structured way for the reader. The code prints labels that identify the span location, material type, and load case. These labels provide context for the engineering data that follows, making the report easier to understand. The code reports key engineering results by printing the span length in feet, the estimated deflection in inches, and the allowable deflection in inches. Including units with each value makes the output clear and suitable for an engineering report. The code checks whether the estimated deflection is less than or equal to the allowable limit. It then labels the result as passing if the deflection is acceptable, or exceeding the limit if it is not. Finally, it prints this status to clearly show whether the deflection meets the requirement. The script produces a clear engineering project report with key identifiers, project context, and deflection results. It lists details such as the project, engineer, location, material, load case, span length, estimated deflection, and allowable deflection. It then compares the estimated deflection with the allowable limit and reports whether the design passes or exceeds the limit. Meaningful labels. Meaningful labels make program outputs easier to understand by showing what each value represents. A number such as 25.4 is only useful when users know whether it refers to a length, a temperature, or something else. Clear labels reduce confusion, make results more professional, and help turn raw numbers into useful information. Labels in engineering software should be clear enough to explain the data without confusion, while still staying concise. Avoid vague terms like value or amount, when a more specific label would better describe the concept. Good labels distinguish similar ideas, such as design load and actual load, and make the data easier for both current users and future reviewers to understand. Consistent labeling makes engineering programs easier to use, maintain, and trust, especially when many people work with them. Clear labels for repeated information, such as material type or test date, help users understand inputs and outputs without confusion. Good labeling turns a script into a reliable engineering tool, while poor labeling can weaken confidence in accurate results. Students should treat labels as part of how a program communicates information for sound decisions. Python code. Meaningful labels. Strings help make engineering values clear and understandable. Meaningful labels reduce mistakes in interpretation, while clear outputs make results easier to use in professional reports. Project information is stored with clear string labels, such as the project name, Riverside Footbridge, the location, North Abutment, and the responsible engineer, A. Rivera. These labels make each value's meaning explicit, helping the data stay understandable and reducing misinterpretation. The setup defines clear labels and floating point values for two beam deflection measurements, the maximum deflection and the allowable deflection, both in millimeters. Pairing each numeric value with a descriptive label helps keep engineering calculations and reports clear and reduces the risk of misinterpreting the results. Create clear report lines for the project, location, and engineer information. Each line uses formatted text to insert the relevant value directly into a descriptive label, making the final report easy to read and understand. The output labels are built by combining clear text with deflection values rounded to 1 decimal place and followed by millimeters. The same formatting is used for both the measured and allowable deflection. A final status message states that the deflection is within the allowable limit, making the result clear, precise, and professional. The code generates a short engineering report using predefined labels. It prints the project, location, and responsible engineer, then reports the maximum and allowable beam deflection values in millimeters to 1 decimal place. It ends with a status message, confirming that the deflection is within the allowed limit, making the report clear and easy to interpret. This Python script creates a clear engineering report by using descriptive labels for project information and beam deflection results. It presents the project name, location, engineer, actual and allowable deflection values with units, and a final status showing the deflection is acceptable. The main purpose is to make technical output easy to read, precise, and suitable for professional documentation. Project information labels. Project information labels in engineering Python programs give calculations and simulations essential context. They identify the related project, component, or system, so results such as stress or flow rate stay connected to their source. This makes outputs clearer and more useful, especially when many analyses are run or shared. In engineering, project information labels help keep work organized, traceable, and easy to review. Professionals often compare multiple scenarios or revisions, so labels such as site names, design options, or condition types make results easier to distinguish. Clear labeling reduces confusion between similar outputs, such as existing and proposed designs, especially when teams share or review the work. When using Python output in reports or presentations, clear project labels are essential. They give raw results context by linking them to details such as the project title or sensor location. Keep labels specific, concise, and consistent with project documents so the output supports professional engineering communication. Python code. Project information labels. Use clear strings to identify the project context and label results so they can be traced back to their sources. Clear, well-labeled output makes engineering communication easier and more reliable. The project is labeled as Oak Street Bridge Inspection, with the site identified as Riverside County, California. The analysis focuses on the proposed repair option. These basic text labels provide clear context and support consistent communication and documentation in the engineering project. The project data is labeled to clearly identify the span 2 steel girder and the service load case being analyzed. A review date of June 8, 2026 is also recorded. These labels help organize the engineering information and make it easier to reference during analysis or inspection review. Two stress values are stored for an engineering safety check. The maximum stress is 18.7 kilopounds per square inch, and the allowable stress is 24 kilopounds per square inch. These values can be compared to confirm the design stays within safe limits. The code prints a short report section for project information. It starts with a clear header, then displays the project name, location, and component label. This organized output presents the key details needed to identify the project and the specific component being discussed. The code prints key context for an analysis, the analysis case, the load case, and the review date. Together, these outputs identify the scenario being studied, the load being considered, and when the results are scheduled for review. The code reports the maximum stress and allowable stress, each rounded to 1 decimal place and labeled in KSI. It then prints a review status stating that the results are acceptable. Together, these outputs present the key stress values and confirm they are ready for engineering review. This script creates a short bridge inspection report by recording the project details, analysis case, component and load labels, review date, and stress results. It reports both maximum and allowable stresses in KSI, rounded to 1 decimal place. When run, it prints the information in a clear, structured format and ends with a status message that the project is okay for review. User input basics. Integer input. User input in Python starts as text, even when it looks like a whole number. To use it in calculations or decisions, the program must convert it to an integer. This is especially important in engineering tasks where inputs may represent counts, such as bolts or test specimens, and must be handled accurately in comparisons, calculations, and reports. Converting typed input into an integer lets a program treat numeric text as a real number for calculations and loop control. Without this conversion, input remains text and can cause errors, especially if the user enters something that is not a valid number. This step is important in fields like materials testing and construction estimating, where accurate numeric input is needed for reliable results. When accepting integer input, make clear what kind of whole number is expected, and check that the value is valid. Counts such as pumps or beams should not be decimals, words, or unreasonable numbers. Clear instructions and validation help prevent conversion errors and unreliable results, which is especially important in engineering applications. Python code. Integer input. This lesson demonstrates how to convert user input into integers using count-based examples from civil engineering. It also shows how to present the converted values clearly in a report-friendly format. A piece of text containing the value 12 is stored to represent user input. Although it looks like a number, it is still text, so it must be converted into an integer before it can be used in calculations such as counting items or measuring quantities. This step converts text that represents a number into an integer. Using the integer conversion function turns the stored text value into a numeric value, so it can be used in later arithmetic calculations, such as totals or lengths. A variable is used to store the length of one beam set to 18 feet. This value can then be used to calculate the total length needed for multiple beams, and it can be changed easily if the beam length is different. To find the total beam length, multiply the number of beams by the length of each beam. The result gives the total feet of material needed for the beams, which supports accurate material planning in engineering projects. This line displays the original text entry along with its data type. It prints a label, the stored input value, and the name of its type, confirming that the input starts as a string before any conversion. This line prints the beam count after converting it from text to an integer, then shows the converted value's data type. Using the type function confirms that the conversion worked and that the result is an integer. This line creates a clear output message for the engineering result. It uses a formatted string to insert the calculated number of beams and the total length in feet, giving a concise summary of the results. This example shows how Python converts a text value into an integer so it can be used in a calculation. A simulated input representing 12 beams is converted from a string to a number, then multiplied by 18 feet per beam to find the total required length. The script also reports the value types before and after conversion, illustrating basic type conversion, arithmetic, and formatted output for a simple engineering-style report. Float conversion. Float conversion turns text input with decimal values into numbers a program can calculate with. This is important for measurements and quantities, such as lengths or concentrations, that are not whole numbers. Once converted to floating point values, the program can perform arithmetic and comparisons accurately instead of treating the input as plain text. Float conversion turns decimal input from text into numbers the program can calculate with. This is essential for measurements such as temperature, voltage, or thickness, where whole numbers are not precise enough. Without this conversion, a program may accept the input but fail to use it correctly in tasks like unit conversion or safety checks. When converting text to floating point numbers, programs must account for user input issues such as extra spaces, commas, or unexpected text. Clear instructions about the required numeric format help prevent mistakes. In professional work, even small input errors can lead to serious calculation problems. So reliable conversion depends on both technical handling and clear communication. Python code. Float conversion. Engineering inputs often include decimal measurements, so text values must be converted to floats before calculation. This conversion makes numerical work more reliable and accurate. User input is first stored as text to mimic real data entry. The span length is represented by the words 4.5 and the load value by 12.75. These text values are placeholders that will later be converted into floating point numbers for accurate calculations. The span and load values are converted from text into floating point numbers, so they can be used in calculations. This makes the span measurement and load per meter available for accurate numerical operations. To find the total line load on a beam, multiply its span in meters by the uniform load per meter in kilonewtons. This gives the total load in kilonewtons, which represents the overall force the beam must carry for structural analysis and design. The code prepares clear engineering report text by formatting the beam span, uniform load, and total load as numbers with 2 decimal places and the correct units. This makes the reported values precise, consistent, and easy to read. The code prints a short report showing the results of a float conversion example. It displays the beam span, the uniform load per meter, and the total load, each rounded to 2 decimal places for clear, readable output. This script shows how to turn text-based numeric inputs into floating point numbers for engineering calculations. It converts a beam span and a uniform load from text into numbers, then multiplies them to find the total load on the beam. The final output presents the span, load, and total load rounded to 2 decimal places, showing how text inputs can be used reliably in calculations. Prompting for values. When a program asks for input, it should clearly state what information is needed, including the unit and required precision. This is especially important in engineering, where the same number could mean different things. Clear prompts, such as asking for a beam length in meters, reduce ambiguity and help ensure the data can be used correctly in analysis. When asking users for input, make the request clear from their point of view. Tell them what kind of number to enter, such as a whole number or a decimal, so the program can store it in the correct data type. Clear input instructions reduce errors and help keep calculations accurate. Clear requests for input values help users trust computational results, especially in engineering, where errors can affect cost, safety, and performance. Each request should give enough context to prevent confusion, such as identifying which temperature or value is needed in a multi-step calculation. The goal is to be concise, specific, and easy to understand, so users enter reliable data and the program produces results that match real-world conditions. Python code, prompting for values. Clear prompts make engineering inputs more reliable, while simulated entries help keep the notebook automatic. Converting values to numbers also prepares the data for later engineering calculations. The code defines 3 prompt messages to collect key structural inputs from the user: beam length in meters, design load in kilonewtons, and the number of anchor bolts. These prompts guide users to enter the right information and make the program feel more like a realistic, interactive engineering tool. The example simulates user input for 3 engineering parameters: a beam length of 6.5 meters, a design load of 42 kilonewtons, and 8 anchor bolts. Each value is stored as text to mimic manual entry, making the process useful for testing or demonstrations. The code prepares input values for engineering calculations by converting them to the right numeric types. beam length, and design load are converted to floating point numbers for precise calculations, while the number of anchor bolts is converted to an integer because it is a whole number count. The code estimates how the design load is shared by the structure. It finds the load per meter by dividing the total design load by the beam lengths, and the load per bolt by dividing that load by the number of anchor bolts. These values show how forces are distributed, supporting structural integrity checks. The code demonstrates a simulated user input sequence by showing each prompt followed by an example response. It asks for the beam length, design load, and number of anchor bolts, using sample values of 6.5 meters, 42 kilonewtons, and 8. This helps illustrate how the input process would appear in a real interaction. The output reports key beam design values with clear units and sensible rounding. It prints the beam length in meters, the design load in kilonewtons, the uniform load as the design load divided by the beam length, and the load per bolt as the design load divided by the number of anchor bolts. These values show how the load is distributed along the beam and how much each bolt must carry for design checking. This script tests a simple beam calculation by using predefined responses instead of manual input. It reads the beam length, design load, and number of anchor bolts, converts them to numbers, then calculates the load per meter and the load per bolt. Finally, it displays the simulated inputs and formatted results, making it useful for checking input handling and basic engineering calculations. Formatted engineering results. Formatted values. Formatted values make engineering results clear and useful in reports. A calculation may be correct, but it still needs to be presented in readable sentences with meaningful labels. Good formatting helps reviewers understand the result quickly and focus on the engineering insight rather than the computation. Computed results should be presented with clear descriptive text, not just numbers. Labels explain what each value represents and help prevent confusion when a program produces several similar outputs. This makes results easier to trace, debug, and include reliably in reports or documentation. Consistent formatting in engineering projects makes results easier to compare and helps anomalies stand out. A uniform structure is especially useful when results are produced repeatedly, such as during design iterations or field studies. Clear formatting is not just a final polish. It supports accurate interpretation, meaningful context, and better technical decisions. Python code. Formatted values. In engineering reports, format values clearly so results are easy to understand. Include labels and units to avoid ambiguity, and round outputs appropriately to keep reports readable and professional. The beam calculation begins by setting the key inputs for a pedestrian bridge check. The beam span is 6 meters, and the applied distributed load is 12.5 kilonewtons per meter. These values provide the basis for later load and deflection calculations. Find the beam's total load by multiplying its span length by the load per meter. For an evenly distributed load, each support carries half of that total. These support reactions show how the beam transfers the load at its two ends. The beam's calculated deflection is 18.7364 millimeters, representing its expected movement under load. This value is compared with the allowable deflection, which is found by converting the span length from meters to millimeters and dividing by 360. This limit helps confirm whether the beam stays within accepted design standards. The report text is built by formatting key project values clearly and consistently. It includes the project name, span length rounded to 2 decimal places, total uniform load rounded to 1 decimal place, and reaction at each support rounded to 2 decimal places. These formatted lines make the final report precise, readable, and easy to interpret. The calculated and allowable deflections are formatted consistently by rounding each to 1 decimal place and adding millimeters as the unit. The check then compares the calculated value with the allowable limit. If it is within the limit, the status is marked OK. Otherwise, it indicates that a review is needed. The code prints a concise engineering summary for the bridge project. It reports the project name, bridge span, total uniform load, and reaction at each support, using rounded formatting so the results are precise and easy to read. The code reports the calculated deflection and the allowable deflection in millimeters, each rounded to 1 decimal place for easy comparison. It then checks whether the calculated value is within the allowable limit. If it is, the result is OK. Otherwise, it signals that review is needed. This script summarizes key engineering checks for a pedestrian bridge. It calculates the total load from the span length and load per meter, splits that load between the 2 supports, and checks beam deflection against the allowable limit of the span divided by 360. It then prints a professional report with the project details, load results, support reactions, and a status message showing whether the deflection is acceptable or needs review. Decimal formatting. Decimal formatting helps engineers present computed results clearly and at an appropriate level of precision. Raw outputs often include more digits than needed, which can make results harder to read or imply false accuracy. Using the right number of decimal places keeps reports consistent, readable, and aligned with engineering expectations. Decimal formatting should match the precision of the data and the needs of the task. Showing more decimal places than the measurement support can be misleading, while too little precision can hide important detail. Choosing the right number of decimals makes results clearer, easier to compare, and more professional. Consistent decimal formatting makes results easier to compare and interpret. Using the same number of decimal places helps readers notice patterns and outliers, while also making reports and tables look more careful and credible. In engineering, this clarity supports reliable communication and better decision-making. Python code. Decimal formatting. Decimal formatting improves the readability of engineering reports, especially when presenting small civil engineering results. Using consistent decimal places makes values easier to compare clearly. The engineering results are stored for later report formatting. Deflection is 7.236847 millimeters. Stress is 182.98721 megapascals, and flow rate is 14.5 liters per second. These values capture the key computed measurements in readable units. Format reported values with clear units and appropriate precision. Deflection to 2 decimal places in millimeters, stress to 1 decimal place in megapascals, and flow rate to 2 decimal places in liters per second. This keeps results concise, readable, and consistent for reports. The code displays the raw results of 3 engineering calculations: deflection, stress, and flow. Each value is printed exactly as computed before any formatting is applied for reporting. Format engineering results consistently so they are easy to read and compare. Show deflection to 2 decimal places in millimeters, stress to 1 decimal place in megapascals, and flow rate to 2 decimal places in liters per second. Clear units and appropriate precision improve the usefulness of the report. 2 centimeter measurements are stored with slightly different precision, then printed using the same 2 decimal format and an 8-character width. This consistent formatting aligns the decimal points, making the values easier to compare in a report. This script shows how formatting numerical results makes engineering reports clearer and more consistent. It compares raw values for deflection, stress, and flow with rounded versions that use appropriate decimal places for each measurement. It also aligns decimal points for span measurements, making values easier to compare. The main point is that careful rounding and alignment improve the readability and professionalism of engineering communication. Engineering units. In engineering, numbers must always be shown with clear units, so their meaning is not ambiguous. A value alone can refer to many different measurements, which can confuse teams working across different disciplines. Proper unit labels in reports and dashboards help prevent errors and make the work clearer and more professional. Engineering units make numerical values clear and prevent mistakes, since the same number can represent very different measurements. Inspection forms, simulations, and program outputs should always label quantities such as mass, distance, pressure, or diameter with the correct units. Clear unit labels support better decisions and help avoid problems like ordering the wrong materials, making unsafe assumptions, or causing confusion between field and office teams. Engineering units should be formatted consistently and clearly to avoid confusion. Do not mix unit systems unless the change is obvious, and label temperatures carefully when Celsius and Fahrenheit may both be used. Keep units close to their values with readable spacing and familiar abbreviations so results remain clear in any format. Clear unit labeling improves reliability and understanding in technical communication. Python code, engineering units. Engineering reports are clearer when results include well-formatted numbers and explicit unit labels. Formatted strings help present measurements cleanly, especially when combining metric and imperial units. The project information is stored as labeled text so it can be reused in reports and documentation. One label identifies the project as a campus walkway drainage check, and another records the responsible engineer as a beginner civil engineer. The code stores key engineering measurements with their units for later use. It records a pipe diameter of 450 millimeters and a channel length of 128.5 feet. These values are kept as floating point numbers so later calculations and unit conversions can remain precise. Convert all measurements to meters before further calculations. Divide the pipe diameter in millimeters by 1,000 and multiply the channel length in feet by 0.3048. Using consistent units makes the values easier to compare and use accurately. Use formatted strings to make the report clear and readable by inserting key details directly into the text. Include the project name, the responsible engineer, and the pipe diameter in both millimeters and meters. Round the millimeter value to a whole number and the meter value to 2 decimal places for a clean, precise presentation. Create a formatted report string for the channel length that shows the value in feet and its converted value in meters. Use 1 decimal place for feet and 2 for meters, and include units with every value to keep the engineering data clear and consistent. The code prints a short engineering report with the key project details. It shows the project name, the responsible engineer, and the pipe diameter in both millimeters and meters. This makes the output clear, informative, and easy to read. The code finishes the engineering report by printing the channel length in both feet and meters. It also notes that every value includes units emphasizing clear and accurate engineering documentation. This script creates a short engineering report for a drainage project. It records the project and engineer names, converts key measurements between metric and imperial units, and prints the results with clear unit labels. The final output presents the pipe diameter and channel length in a readable format, making the report clearer and more professional. In this lecture, you learned to use strings to label engineering inputs, outputs, and project information. Collect user input and convert it into numeric values for calculations. And format computed results so they are understandable in engineering reports. In the next module, Module 2, we will go over control and logic. Thank you for your attention. See you all in the next lecture.